Hi folks, in this video I document how I built my own flexible solar-powered DIY 3-port 18-volt Ryobi SuperCharger. And let's get it up to about 21.5 volts. Each of these supplies Hi folks, Dave here. In this video I'm going to show you how to build a 3-port direct DC solar charger for Ryobi 18-volt batteries. The idea scales up well, even a 4 to 8-port charger would be possible. I chose 3 for this project. A pair of 100-watt solar panels powers the charger all day for free. No DC to AC inverter is required. There are minimal electronic components, and the DC converters are fairly simple, cheap, possible to repair if needed, and very flexible. By lowering the power settings, it could certainly function on a single 100-watt solar panel. For this project I am again using the Ryobi PCG002 battery charger because it is readily available. It also accepts a DC input supply. This is the same charger I used in my last Ryobi solar charger project. One of the goals of this project is to demonstrate the viability of what I call PV to load, the concept of attaching useful devices and appliances directly to the PV solar array. Cutting out the battery, charge controller, and inverter could reduce costs and increase efficiency. In this simple diagram you can see that the idea is to eliminate the charge controller, the battery, and the inverter and use only a solar panel to do the work. Of course you could eliminate only the inverter and keep the charge controller and the batteries. A lot of my DIY prototypes and projects are intended to run off of solar panels directly, such as this small oven here, linked in the description. The charger can still accept a standard 12 to 48 volt input from a battery bank if needed. The first part of this video shows the build steps I used to build this charger, and the second part is a technical explanation of using DC to DC converters in an application like this with solar power. And I'll include some clips of the charger in operation. If you like this video, please let me know and leave a thumbs up. Thanks for watching. order to run this charger off of solar panels and charge 3 separate batteries, I'm going to need 3 separate DC to DC converters. I'm going to explain why that is. I'll just draw the sun here, and we'll put some solar panels here. Let's assume they're putting out about 40 volts DC. Let's assume they're in series, and let's draw them like this. We have 40 volts DC, sun's shining, and we want to drive 3 18-volt chargers using this power supply. This power supply could vary in voltage. It might be 50 volts, it might be 30 volts, and we have to make sure that the voltage is stable and powers the chargers. In order to do that, it's going to require 3 DC converters. If I start with just one DC converter, let's go ahead and just draw one here. And let's just assume that 40 volts is going into the DC converter, and you're getting 18 volts here. In addition to that, I've set it to 2 amps constant current, and that's to protect the charger, protect the battery, and basically to make sure that there's no safety problems. And you have your Ryobi battery, which is right here. Let's just go ahead and draw it. And the DC converter is charging it through the charger, of course, and everything's fine. But what if you wanted to charge 2 batteries, or maybe 3, or possibly even 4 batteries from the same solar panels? You might think that all you have to do is just take your DC converter here and attach it to a second charger. But that's actually not going to work. The reason is that this supply, which is really going to be more like 22 volts or so, the charger is going to pull this DC converter down to whatever voltage it's at. So let's say, for example, this battery here is deeply discharged and it's 15 volts. What's going to happen is this battery at 15 volts is going to pull this DC converter down to about 15 volts. So you're going to be operating at this voltage right here while the battery slowly charges up. It's going to start slowly rising up, but it's going to take a while. If I try to attach another charger here, and let's say I put in a battery, and let's just go ahead and draw the battery, and let's say that it was at 20.5 volts. So now we have a second battery we want to charge. But this voltage supply has been pulled down to 15 volts. This DC converter is supplying about 15 volts at 2 amps, and this voltage is slowly rising, but it's nowhere near 20.5 volts. What's going to happen is when I connect this nearly full battery to a second charger, if I tie it into this DC converter here, it won't charge, because 15 volts isn't going to charge a battery that's at 20.5 volts. And this DC converter is busy right now putting out 15 volts and powering this charger. It's putting out about 2 amps. It's a constant current supply, which is ensuring that it only puts out 2 amps. In order to only put out 2 amps, it has to drop to 15 volts. That's just how it works. Therefore, I can't attach my second or third battery to the same DC converter. It isn't going to work. But what will work is if I take another DC converter and I tie that into the same solar panels. And I've got another 18 volt supply here, 2 amps. It's the same as this one. And now it can serve this charger, and it can put out about 20.5 volts at 2 amps. And this idea scales up really well. If I want to, I can go ahead and add a third DC converter, and I can go ahead and tie that into the solar panels like so. And now I've got 3 DC converters and 3 separate supplies in operation here, and I can charge 3 separate batteries. And it doesn't matter now what the voltages are, because each of these supplies here will regulate to whatever that voltage needs to be at to charge the battery that's connected. If it's a different one here or here, it won't matter. The downside is you need 3 times the converters. However, you're charging 3 batteries simultaneously from only one set of solar panels. Therefore, this kind of a configuration is actually quite useful and actually makes a lot of sense. What we're going to end up with here is 3 regulated outputs and 3 separate chargers charging 3 different batteries, all from one set of solar panels, or even a single solar panel if you use one that's big enough. All of these DC converters that I'm going to be using, they look like this, are DC to DC converters with constant current and constant voltage. Now, to explain how that works, this DC converter can take a DC input voltage and it can output whatever you set it to. So for example, I could put in 35 volts on this side and I can get 21 volts on this side, whatever I set it to. I could put 12 volts in here and get 21 volts here. I would still get the same voltage because this converter is actually a buck converter and it's a boost converter. To explain the difference, a buck converter drops the voltage. And it's always going to drop the voltage. You can't do anything else. And that's actually very useful. This converter here is actually a buck converter. However, there's also a boost converter. And a boost converter is actually also extremely useful because it can raise the voltage. So a boost converter raises the voltage and a buck converter lowers the voltage. This converter does both. So it actually has both capabilities built in. What this effectively means is your input voltage, which is going to be on these terminals, can be anything. It could be 12 volts, 10 volts, 50 volts. This particular one can accept as much as 50 to 60 volts. And on the output, you can continue to have whatever you want. You can have 18 volts or whatever you set it to. In the case of a Ryobi battery charger, it needs to be about 21.5 volts, 22 volts, or something like that. So this board here is actually known as a boost buck converter or buck boost converter because it does both. It's got both sets of circuits on there, and it means that you can now disconnect the output from the input in terms of voltage. You can use any voltage you want and still get the same results on the output. All of that is within reason, though. It's not possible to get power out of thin air here. This thing is just going to take what it has and work with what it has. It's going to waste a certain amount of that power, maybe 5%, in doing this conversion, but it's very useful because it can do what's called impedance matching. So it can match the impedance of your output to the load that you're running. A battery has very low impedance usually, and a solar panel would have relatively high internal resistance or impedance, and so you would waste power by just attaching the solar panel straight through. In addition to that, it would not be possible to charge 3 separate sets of battery with just one solar panel if you want to do that efficiently. This is a more efficient solution overall, if you take everything into account. Now I'm going to show you how to set these power supplies up. It doesn't matter which one you use. This is just the one that I prefer to use. I've used it in a number of projects, and I like them. These boards are actually sold as LED drivers, but they can do other things as well. It has another feature built in, as you can see. It has 2 trim pots on it. One is for voltage and one is for current. I'll go over that more later in the video. Constant current. What is constant current? This board also has the feature of constant current and constant voltage. So constant voltage just means that you set the voltage to what you want, and it will try to maintain that voltage no matter what you put on the input. This board also has what's called constant current. Constant current is extremely useful because it allows you to control how much power flows through this board no matter what. As you know, voltage times current, or amps, is watts. What we're going to do is we're going to set the constant voltage on this board to about 21.5 volts. However, there's a problem. If I put 2 big 100-watt solar panels on this board, potentially I could have a problem with this board burning out, or I could harm the battery, I could cause a fire. Who knows what would happen? This board not only limits the voltage, but it has constant current, which means it could control the current as well. And I'm going to set mine to around 2 or 3 amps. So how does a constant current board respond to a condition where it needs to limit the current? The answer is when the current starts to get too high, it will drop the voltage to reduce the current. In early days of testing this charger, 2 amps is good enough, so we'll make it 2 amps. And that's going to be right around 40 watts. Which is certainly a nice charge into the battery. It's not super fast, but it can be made faster. I'm going to err on the side of caution, and I'm going to program my boards to be 2 amps, and later on I can put them up to 3 or 4 amps if I choose to. It's not a problem. You can recognize this board as having both features because usually there will be 2 trim pots, one for voltage and one for current. And I will show you how to adjust these boards to put out the right amount of current and voltage. Let's briefly review the difference between a buck converter and a boost converter. This board is actually both. A buck converter could take, let's say, a 24 volt source and convert it to 12 volts DC. And you could run a 12 volt load off of a 24 volt power supply by using a buck converter, which always drops the voltage. But a boost converter, for example, could take a 12 volt battery and boost it up to 24 volts, and you could run a 24 volt load from a 12 volt battery. A boost buck converter, which is what this is, has both capabilities built in. It's a little more complicated, but it's extremely useful with solar power. You may use different solar panels, the conditions may change, you never know what the voltage supply will be. This board can both raise and lower the voltage independent of the input, and that's why I chose this board for the project. In order to get this board working properly, I need to set it to the proper voltage on the output as well as the proper current. How do I do that? Well, I'm going to show you right now how to do that. In order to test this board, this is a brand new board that I just got. I need to go ahead and hook it up to a power supply, and I want to set the voltage output and the current. So let's go ahead and do that. Alright, first step is going to be to power up this board using my bench power supply, or you can use a solar panel. I normally use a solar panel, but today I'm just going to use the bench power supply because that's more convenient. I'm going to go ahead and make sure the output wires are not shorted. I'm going to take the bench power supply, connect the positive and negative, and it powers up. You can see the blue light, which is illuminated on the board. That means it's turned on. Now let's find out what this board is set to in terms of output voltage. I'm not going to connect a load to it yet. I've got my multimeter in the upper left hand corner connected to these clips, and I'm going to go ahead and measure the output. And you can see I'm getting 24 volts. So this was set from the factory at 24 volts. It's a brand new board. 24 volts is not the correct voltage for my project, so I'm going to go ahead and adjust that. Now we need to identify how to adjust the voltage, and it's very clearly labeled on the board, CV. You see the letters there where I'm pointing. And there's a little arrow going around the corner, and that's pointing at this trim pot here. That's actually the constant voltage supply adjustment. For constant current, there's actually two letters, CC, which is right where I'm pointing, and that is actually got a little arrow pointing at this trim pot here, which tells me that this bottom one adjusts the current. I'm not going to touch the current yet. I'm going to go ahead and change the voltage to be whatever I want it to be. In this case, for the Ryobi SuperCharger project, I want to use about 21.5 volts. I'm going to go ahead and change the trim pot here to correct the voltage to 21.5 volts instead of 24. Let's go ahead and do that. Now, in order to change the voltage, generally speaking, I've found that you have to turn it clockwise to get less voltage. So I'm just going to go ahead and turn this clockwise, and indeed the voltage drops. Let's now turn it to the left, which is counterclockwise, and let's get it up to about 21.5 volts. It only takes a little bit of turn on the trim pot to get a change. You have to be very precise. Yeah, it's close. And I managed to get it pretty close to 21.5 volts by adjusting the trim pot very carefully, and that part is done. The next thing I want to do is I want to adjust this board to 21.5 volts, and also I want to put out 2 amps. How do I do that? Well, I'll show you how I do it. There's probably other ways to go about this, but I'll show you my tried and true method that I've used for years. I'm going to turn the trim pot to adjust current all the way to the right until the board stops putting out voltage, and that's going to tell me I've hit the lower limit. So let me go ahead and do that. I'm going to keep turning the current adjustment trim pot to the right a little bit at a time until I see the voltage drop on the output. And it just dropped. That means I've hit the minimum current. Now I'm going to turn it to the left about a half a turn, and it goes back up to 21 volts. So the current is effectively set to pretty much the minimum right now. And what I need to do is put a load on this and adjust the correct current level. What I'm going to do is I'm going to take this resistor here, it's a power resistor, and an amp meter, and I'm going to put that across the output and use it to basically set the current to the value that I want. Okay, I have my trusty GE2524 multimeter here. I love these meters because when you turn them on, they stay on until the battery runs down. They don't beep. They're not smart meters. They just do a good job and they work. If you're interested, I have 2 great videos linked in the description about using a digital multimeter with solar power. It covers an extremely broad variety of DIY and entry-level topics, as well as intermediate and somewhat advanced topics. There's 2 separate videos. One is using the GoChiFix Smart Digital Multimeter, which is over here on the left. And the other video, which is also very good, is using this GE multimeter, a very basic meter that does a really good job. I really highly recommend you watch both of those videos if you want to learn about using a digital multimeter and you want to expand your knowledge and skill sets. First thing I'm going to do is I'm going to take this multimeter here and I'm going to set it to the 10 amp range. I'm going to wait for it to 0. It takes a while in this meter. There it goes. Now that it's zeroed, I'm going to take the red lead out of the socket for volts, ohms, and milliamp, and I'm going to put it in the 10 amp location. It's important to remember that this is a short circuit through the meter. As soon as you're done measuring current, you need to take this out and put it back in the volts socket. And that's covered in my video about how to use a digital multimeter, and I actually use one of these very meters to make that video. Alright, let's go ahead and measure current using this meter. You can handle up to 10 amps, that should be enough. What I'm going to do is I'm going to take the connections on this meter, those are right here, and I'm going to connect a power resistor to it. So I've got a power resistor on one lead, and I've got the other lead here, and I'm going to attach that to the output, which is right here, and I'm going to see how much current I get. Now this is kind of a short circuit, but it's not a short circuit. It's got a resistor, this resistor right here, and so I like doing it this way instead of just shorting it out with a pair of wires. I like a little bit of resistance in there in case something goes wrong. Alright, let's go ahead and take this resistor and this amp meter and let's place it across the terminals, positive and negative, and see what happens. Alright, you can see the output voltage collapse and I got like 30 milliamps, so obviously the current is way too low. So let's go ahead and raise that. Now in order to get this board to supply the current I'm looking for, I had to raise the input voltage to about 29 volts, and I'm not surprised by that or terribly concerned about it. Some of these boards simply cannot provide the current through a resistor like this when you're attempting to adjust them. I'm not too concerned about it. I wouldn't normally just short a resistor across the output anyway. I just want to check the current and make sure it's set properly for my application. Let me go ahead and turn the trim pot on the current, and I'm going to connect the resistor. You can see I'm getting about 60 milliamps. I'm going to turn it to the left a little bit. Now I'm up to 300 milliamps. Okay, I'm going to go a little bit higher than that. I want 2 amps. It's actually hard to adjust the current because it's very sensitive. The slightest turn changes the value. So I'm going to try to hit 2 amps here. And there's 2 amps. Now I'm going to go ahead and disconnect the resistor. You can see that it was putting out 2 amps. Alright, I have this board set to 21.5 volts and about 2 amps of current, and it's ready to go ahead and be used in the project. I took this charger outside in my yard for its maiden test. I configured it to work with 2 of my favorite solar panels I use for outdoor applications. They're 100 watts. I found this Ryobi charger to be very lightweight and easy to carry. With the DC converter set at a relatively mild power setting, I was able to hit 136 watts into 3 of my Ryobi 18-volt batteries. The fans did a good job, and I should be able to get more power through this setup if I want to. One of the things I like about this setup is that the DC-DC converters are tunable and you can set them to any power output that you want, even having 3 different power levels, and that allows you to configure and customize how you charge your batteries and what kind of solar panels you use on a daily basis. This setup turned out to be pretty much plug and play. I just put my solar panels up, plug them in, put the batteries in, and off they go. As long as the sun is shining, I can charge 3 batteries. If the sun gets a bit dim, sometimes I'm limited to only 2 or only 1 battery, but that's to be expected. Please leave a thumbs up if you enjoyed this project. Thanks for watching and hope to see you next time.